Section 2. Waves transfer information. Using satellites to navigate. Turn left and then continue straight. If you've ever used a smartphone or a car's navigation system, you have communicated with satellites orbiting about 20,000 kilometers or 12,600 miles above Earth's surface. The best known navigation satellites in the United States are part of GPS, which stands for the Global Positioning System. GPS works by using 24 satellites that orbit Earth once every 12 hours. These satellites send information about a location that can tell us exactly where we are. Waves. To understand how satellites far above Earth can provide your exact location on the ground, it helps to understand waves. A wave is a disturbance that travels through space and/or matter, transferring energy as it moves. People can use waves in a variety of ways, including in GPS, cell phones, radio, microwaves, and CDs. Most waves fall into one of two categories: light waves, also called electromagnetic waves, and mechanical waves. We'll explore how waves are disturbances and the differences and similarities between the two categories of waves. Waves and matter. Picture a slinky. If you stretch the slinky out from end to end and then move the first coil up and down or from side to side, a wave will travel from that end of the slinky to the other end. The waves in a slinky are mechanical waves because they are caused by vibrations in matter. Remember that matter is anything that has mass and takes up space. This matter is called a medium, and it can be a solid, a liquid, or a gas. For example, rock is a solid medium, as is a slinky. Water is a liquid medium, and air is a gaseous medium. As mechanical waves travel through a medium, they cause molecules within the matter to bump into each other. As this happens, energy transfers from one molecule to the next. It is important to note that waves don't carry matter. After the energy moves through, each coil of the slinky will return to its original position. Another common mechanical wave is caused by raindrops on a still lake. The kinetic energy of the falling rain transfers to the water, which creates water waves that carry that energy as they ripple outward. Once the ripples die down, the water returns to the same position. Sound waves are another form of mechanical waves. Picture a person blowing into a trumpet. The energy of the person's exhalation causes nearby air molecules to vibrate and bump into the molecules closest to them. This contact passes on the energy and makes them vibrate too. Then those molecules bump into more particles and so on. Particles stop vibrating once they have passed on the energy. Light waves. Unlike mechanical waves, light waves do not need a medium to travel. A light wave is a pattern of light energy that moves at a constant speed until meeting matter. Remember that the sun transfers energy to Earth through radiation, heat transfer that occurs without contact between the heat source and the object heated. That energy travels to Earth in light waves. Exactly how light waves travel is very complex, and scientists have many unanswered questions. However, scientists do know that light waves can travel through a vacuum because the sun's light reaches Earth through the vacuum of space. A vacuum is a space that has no matter in it. In contrast, sound cannot travel through the vacuum of space because there are vast empty regions between matter in space, which means that molecules are too far apart to transmit the energy. There are many kinds of light energy. Microwaves are used in appliances to heat up your food and in satellites for communication and navigation. X-rays are used at the dentist to capture images of teeth and at the airport to see through bags. The type of light energy depends on the amount of energy in the different waves. Radio waves have the lowest energy. Your radio captures radio waves that are sent out by radio stations. As waves move, they create a disturbance. This is true for both mechanical waves and light waves. Picture the pebble being thrown in the lake. The waves ripple outward, creating a disturbance in the water. However, not all waves create a disturbance that moves in the same direction. For example, in some waves, the disturbance moves perpendicular to the direction of the wave itself. In other words, if the wave moves from left to right, the disturbance moves up and down. This kind of wave is called a transverse wave. When a crowd of people in a stadium do the wave, they are modeling a transverse wave. The individual people move up and down while the wave moves from left to right or right to left. This is another example of how waves move energy, not matter. After the disturbance passes through, the people go back to where they were before the wave moved through. Light waves are also transverse waves. Longitudinal waves. In some waves, the disturbance moves parallel to the direction of the wave itself. If the wave moves from left to right, the disturbance also moves from left to right. This kind of wave is called a longitudinal wave. Sound waves are longitudinal. As sound waves move through a medium, the molecules of the medium collide with one another in the same direction the sound wave is moving. Patterns in waves. All waves represent repeating patterns. This can be understood by thinking about the anatomy of a simple wave. The wavelength is the distance spanned by one cycle of the motion of the wave. In transverse waves, it is usually measured as the distance between two crests, the top of the wave, or two troughs, the bottom of the wave. In longitudinal waves, it is measured as the distance between compressions, point where the molecules are pressed together, or rarefactions, point where the molecules spread out. Amplitude and frequency. The amplitude is a measure of the wave's displacement from its resting position. For example, in a water wave, its amplitude is its height above the water's surface. In a mechanical wave, the amplitude is proportional to the amount of energy carried. This means that if the amplitude of a mechanical wave is doubled, each wave will have 4 times as much energy. In a light wave, the amplitude is related to its intensity, which we see as brightness. A light wave with a higher amplitude will be brighter than a light wave with a lower amplitude. The frequency of a wave is the number of waves that passed a set point in a given amount of time. A wave with a greater frequency also has a shorter wavelength. If you look at the electromagnetic spectrum diagram on page 22, you'll notice this pattern. Radio waves and microwaves have long wavelengths and low frequencies. X-rays and gamma rays have short wavelengths and high frequencies. Waves that have low frequencies and long wavelengths carry less energy than waves with high frequencies and short wavelengths. Remember that radio waves have the least energy of all electromagnetic waves.